Hello and welcome to ECMath. Today we're going to look at section 3.1, which is about exponential functions and their graphs. We'll also talk about the number e, compound interest, and look at some graphical transformations. To warm us up, before we get into too much about functions, I'd like you to take a second and look at these three tables of values. We'll call them F, G, and H, and maybe pause the video for a second and think about if you see any patterns that you notice between these three tables. So when you have a table of values, one thing you might choose to look at is the differences between terms. That is, what happens when you subtract consecutive terms. So 4 minus 1 is 3. That is, we're increasing by 3 for every increase of x by 1. Let's go ahead and fill in all the differences for all the terms in this table. All right, so there's some differences. We notice right away that the first table has a constant difference, and if we were talking about sequences, we'd call this an arithmetic sequence, but if this is a function, we'll call this a linear function. Linear function like mx plus b, if we have a b value and a slope, we could probably find the equation, maybe something like y equals 3x, that's the difference, plus 1, the initial value. So that's a pretty easy equation to find. For g of x, we don't have a constant difference, but there is this pattern of the differences so that every difference is increasing by 2. When you have the second order differences increasing constantly, that's going to give you usually some kind of quadratic function. So y equals something, this looks like maybe x squared plus x, which you could factor into x plus 1 times x, so like 30 is 5 times 6, 4 times 5 is 20, 3 times 4 is 12, 2 times 3 is 6, x plus 1 times x. Quadratic function, constant differences. But then I got to the third function, and I started looking at the table, and I didn't notice a pattern in the differences, and I didn't compute the second order differences because there's a lot of decimals, but I don't feel like I'm noticing a pattern there either. And in fact, there should not be a pattern, because this third function is special. This third function is not a linear function or a quadratic function, it's an exponential function, which is the topic of today's video. And when you're looking at an exponential function or you have a table that you suspect is exponential, instead of looking for a constant ratio, you should be looking for a constant multiple. So instead of plus 3, this is times 1.5. Times 1.5, and we are repeatedly multiplying by the same value every time. So an equation for this might be 1.5 to the x. I think it's just that simple one because we start with x equals 1 and h equals 1.5. So that seems like a pretty basic, good exponential equation with a base of 1.5. And like I said, this is the topic of the video today. So let's keep looking at some of these properties of exponential functions, what makes something exponential, and all of that. So exponential functions are a little bit different than other parent functions because you can have many different bases and they all sort of have a similar graph, and we all call them exponential functions. So the key idea for an exponential function is that you have f of x equals b to the x. B here, I know they both look like letters, but B is a constant, and X is the variable. So the key feature of an exponential function is that you have X in the exponent. Nowhere else. If you have an X not in the exponent, you're not looking at an exponential function. So X is X. B here is called the base, and there's two rules about the base. First, you can't have a base of 1, because the equation y equals 1 to the x, well, you can think about what that would look like. Seems pretty boring. Also, the base must be larger than 0, because if you have y equals negative 2 to the x, you're going to run into some weird issues with negative exponents, negative numbers to fractional powers. Remember, for example, that you can't take, say if x is 1/2, negative 2 to the 1/2 is imaginary. So you can't have a negative base because that's taking you to imaginary town. since x can be any number including fractions or negatives. But one thing that people sort of mistake is they think, then the base must be a whole number, 1, 2, 3, 4, 5. That is also false. The base can be between 0 and 1. It just can't be less than 0 itself. And in fact, the family of exponential functions where the base is between 0 and 1 has a distinct shape that we'll look at in a little bit. So here are some examples of functions that are, yes, exponential. I'm just going to use y equals instead of function notation, but you could also call these f of x. Y equals 2 to the x is an exponential function. So is y equals 10 to the x. That's an exponential function. So is y equals 0.2 to the x. So there's our example of a base less than 1 but greater than 0. And you can also have transformations of exponential functions. So you could have negative 0.7 to the x minus 3. That also counts as an exponential function because you still have that variable in the exponent. You have a definite base. You just have some other transformations going on. Those are all exponentials. Here are some things that are not exponential, that are frequently counted as being exponential. Two of them break the rules of bases. We'll start with those. So y equals 1 to the x does not count or is not considered an exponential function because it breaks the rule of the base. Same with y equals negative 5 to the x. You can't have a negative base to be an exponential function. So those guys are right out. However, also not exponential is y equals x squared. We know what this function is. We know it's a parabola. We know it has a graph that looks like this. But the left side critically does not behave in an exponential way. And also, this is a polynomial, not an exponential function. So when we say something's exponential, we need the variable to be in the exponent and the base to be in the base. And this one, x squared, has the variable in the base, and the 2 in the exponent, that's not exponential. Another non-exponential function that sometimes fools people is y equals x to the x. That does solve the problem that we wanted the variable to be in the exponent, but it also has a variable in the base. X to the x is not an exponential function. Either that actually grows faster than an exponential function, and we are not dealing with that right now. So non-exponential functions right here. And I'm just going to end this section with a plea to you. Please use the word exponential correctly. So this is something that gets used wrongly in the media so much. Media, student papers, teachers, everyone uses this wrong. You can be the people that stop it. Just because you have something growing rapidly does not mean it's growing exponentially. Here are some creative suggestions that you can use to describe rapid growth that's not exponential. You can also, if you know the function is, say, quadratic, say something's growing quadratically, or cubically, or linearly. You can be precise. That way, everybody knows that you know what you're talking about. So why do I harp so much on using the term exponential right? It's because exponential growth is really important because it's very, very rapid. So here are our 3 tables from before. Remember, we had a linear, we had a quadratic, and here we have an exponential, which was y equals 1.5 to the x. And we had the equations for the other two above. Right now, when x is 5, the linear function just puttering along, and it's just going to do its linear thing. The quadratic function is all the way up at a value of 30. That's pretty big. And our poor exponential function's only over here at 7.59. But I have more values, thanks to the magic of spreadsheets. I have a couple more lines, and let's keep going. Let's keep looking. All right, so our quadratic function is growing quite a lot, right? We're at 11 now. We're at 132. And the exponential function's kind of keeping pace at 86. Linear function is left in the dust at 34, right? It's over there doing its own thing. The quadratic function is growing more and more steeply, but remember the difference is only increasing by 2 when we look at the second order. So it's only going to grow by like 2 more than the previous amount every time. On the other hand, this one is actually multiplying by 1.5 every time. And even though 1.5 is not a very big number, this is going to be more faster. Sorry, words are hard. You know what I mean, folks. Let's go. All right, so we're revealing a couple more slides here. And by the time we get to slide 25, you just can see just how dramatically the exponential function has taken over. The exponential function is at 25,000. Well, our good old friend, the quadratic function, is at 650, and our linear function is over here being sad at a value of 76. That's what's going on. And it only took, can we find out where they actually cross or intersect? So we have here the exponential function's right ahead, or the quadratic function's ahead, and here the exponential function is ahead. So by the time x equals 13, we have 1.5 to the 13th is greater than, I think the equation was 13 squared plus 13, x squared plus x. So already our exponential growth is outpacing quadratic growth, even though 13 is not a very big number, right? And think about all the numbers. 25, not very big, considering all the possible inputs that we could be thinking about in a graph. Exponential growth will always outpace polynomial growth of any kind. Even if this was an, x to the 10th, exponential growth will eventually win. It always will win. Let's look at the graphs of the exponential parent function. And I'm going to separate this into two graph situations. The first is if the base is greater than 1, and the second is if the base is between 0 and 1. So there'll be two slightly different graphs. So the example might be something like y equals 2 to the x here, and this might be y equals 1/2 in parentheses to the x. But I'm not going to graph that specific one. We're going to be kind of a little more general. So we're going to graph just b to the x. So here are the key points on a b to the x graph. If x is 0, b to the 0 is equal to 1. So when x is 0, we will always have the point 0, 1, no matter what b was. That point will be in every exponential graph. When x is 1, b to the 1 is equal to b. So depending on the base, when we go over 1, we'll go up b. And it looks like b is between 2 and 3 here. And then the third, maybe a third point is if x is 2, b squared, well, that's just b squared, so that would be a little further up if x is 2. Now, 2 comma b squared doesn't start to fit on a lot of graphs. These will grow quickly, so instead it can be better to go the other way and consider negative numbers for x. Remember, the domain of these is all real numbers, so we have to put in positives and negatives. So if x is negative 1, b to the negative 1 is the same, remembering fractional exponents, as 1 over b. So if b is like between 2 and 3, this would be like between 1/3 and 1/2. So somewhere over here. So that's the third key point. Negative 1, 1 over b. These 3 points, 1, 2, 3, should be on every exponential plot graph you graph. Now, the exact locations of the blue and black points there will depend on the base you choose, or the base you're given. But the 0, 1 point will always be the same. And another thing that will always be in every exponential graph is a horizontal asymptote. Every exponential graph has a horizontal asymptote of y equals 0, and you must plot that for every exponential graph. I'm using kind of a squiggly line because it shows up better on the computer. You can plot it with a dashed line as well. And I'd encourage you to start labeling it with its equation y equals 0. So what does the graph look like? Well, starting at 0, 1, we grow to the right with increasing steepness. And as we go to the left, we shrink down, we hit that 1 over b point, and we approach the asymptote. Why does it approach this asymptote over here? Well, think about it. If this is negative 1, negative 4, then we're looking at y equals b to the negative 4, which is 1 over b to the 4th. Since b was a number bigger than 1, this is going to be very small. However, it will never cross the asymptote because there's nothing in 1 over b to the fourth that's going to cause it to be 0 or negative. Since the base isn't 0 and the exponents aren't 0, there's nothing here that's going to actually create a 0. This is always going to be above, but getting closer and closer to this horizontal asymptote. By the way, just one interesting fact. Remember when we studied rational functions, we had horizontal asymptotes that were always the same to the left and the right. If your right side asymptote was 2, your left side asymptote was also 2. Exponential functions, of course, are different. Only one side has a horizontal asymptote, and the other side has growth, unless it's reflected or whatever. The other side will not have that asymptote. It will trend towards positive or negative infinity. All right, now what if we have a fractional base value? So thinking about something like 1/2 to the x. Well, if x equals 0, b to the 0 is still 1, so we still have the key point 0, 1. And we still, now if x is equal to 1, we still have 1 comma b, but remember that b is less than 1, so 1 comma b ends up being a fraction itself. And on the other hand, if x is equal to negative 1, b to the negative 1 is equal to 1 over b, but since b was a fraction, 1 over that fraction should be bigger than 1, right? Like 1 over 3/4 is 4/3. So here we're going to have 1 over b being a number bigger than 1. We still are going to have a horizontal asymptote in the same place at 0. Make that a little more flat. There we go. But the graph will look like this. Include arrows in both ends. Label the asymptote. 3 key points. Let me highlight those. 1, 2, 3. Let me highlight the key points over here also. And the situation, to put these side by side, the situation on the left is called growth because it is growing. And the situation on the right is called decay because it is shrinking. And, we say not shrinking, but we say decay always refers to this specific kind of growth where it's shrinking, but never actually going negative. It's just approaching 0. Now, exponential growth and decay have a lot of really similar properties, but we are going to go through the domain and range and sort of graphical properties, and whether they are the same, we'll just say same. So for the domain of both exponential growth and decay, it is all real numbers. That is, any x is a valid input. For the range, that's the y values, it is always y greater than 0, or in interval notation, 0 to infinity. Notice, critically, strictly greater than 0, not equal to 0. Neither of these two graphs cross the y-axis. The y-intercept for every single one is 0, 1, unless it's been transformed. But of these two parent functions, both have the same y-intercept of 0, 1, and they go through key points. I said one other key point. We'll say 2 other key points, 1 comma b and negative 1 comma 1 over b. And that applies whether the base itself is a fraction or a number bigger than 1. It's just how you plot those numbers will be different. We can look at the vertical and horizontal line tests. Notice that both are passed. Both. Which means the vertical line test says that y equals b to the x is a function. Check. And it has an inverse. If you are paying careful attention in your previous math classes, you might already know what that inverse is. It's y equals the log base b of x. So we will be eventually, when we talk about inverse functions, thinking about the logarithm as the inverse of the exponential function. But that comes later. Symmetry? None. And asymptote slash end behavior, it does have a horizontal asymptote. Of y equals 0, but it's only on one side. And on the other side, the end behavior approaches infinity. Now, which side that is depends on if you're looking at growth or decay. Here's a quick test for you. See if you can decide whether these four functions determine exponential growth or exponential decay. Have you had a chance to think about it? Great. Let's look it over. So 10 to the x is going to represent exponential growth. It's going to be a graph that looks something like this. It's going to go through the point, 1, 10 as its secondary point. 1/10 to the x, that's going to represent decay. I should put that down here. Those are kind of what we expect. But there's two other ways that you might see a graph, or one other thing you might see, I guess I should say, which is what if there's a negative in the exponent? Now, technically, this is a transformation. You could think about this as a reflection, but we can also think about negative exponents using negative exponent rules. So 10 to the negative x is like 10 to the negative 1 to the x. So that's the same as 1/10 to the x. So 10 to the negative x actually also represents decay. Because algebraically, it's equivalent to 1/10 to the x. These two graphs are the same. So yes, you usually see decay represented with a fraction inside the base, but sometimes you might see a whole number base and think that's going to be growth if you're not paying attention to the negative on the exponent. If you have a whole number base and a negative exponent, you're actually looking at decay. And then on the other hand, if you have a fractional base and a negative on the exponent, it's kind of like a double negative. And this is actually going to represent growth again. Now, this doesn't happen very often unless you're like in the middle of a math problem. But this is the same as 1/10 to the negative 1 to the x, which is the same as 10 to the x. So this is actually going to be the same growth as 10 to the x. So you're looking for sign of the exponent, and do you have a fractional base? And that's how you can tell growth versus decay apart. Here's a quick sidebar about a really important application of exponential functions. Exponential functions model disease spread. So basically, if you imagine catching a disease, you might have a certain percentage chance to spread it to another person, but you kind of look at the average number of people you spread something to. So if I catch a disease and I'm able to spread it to exactly one person, then we're just going to increase linearly. And that number of people you spread the disease to is called the R value. And that's actually what epidemiologists will look at to decide, like, is a disease going to get worse or is it going to die out? So if the R value is 1, you'll have sort of a linear increase in cases because you're multiplying by 1 only. However, if the R value is greater than 1, maybe because the disease is just a little more virulent or it's a new variant or something, then now each person on average is going to infect more than one person, right? So I have one person, on average I'm going to infect 1.1 other people, but then on average more people are going to get infected, and you're going to have basically an exponential base of 1.1. That's growth. On the other hand, if you're trying to mitigate the effects of a disease and make it spread less, you might put on a face mask or take other precautions. And the main reason that you do these precautions is to limit that reproductive number to something like 0.9 or 0.5. Why? Well, because if you have an exponential function, 0.5 to the x, that's actually going to give you exponential decay. The number of people infected will go down. Now, this graph is still showing an increase because it's representing a total of infections, which is something you would be concerned about. But notice that the trend of the increase is slowing because the number of new cases in this hypothetical scenario would be going down because it is representing exponential decay. So really important to think about exponential, the difference between growth and decay when you're thinking about something critical to our current everyday life, like the spread of a disease. And just obviously this graph and what I've just said is a huge abstraction of what epidemiologists, really do, because you have to worry about things like people get sick and then get sick again. People get sick and then get better. Do they have immunity, right? All of these things are going to play in. This is just saying kind of initially from day zero as something is first spreading, that R value is really, really important if you want to keep your disease under control. Okay, so we know what the graph of exponential parent functions looks like. Let's talk about transformations. It's maybe been a while since we've transformed any graphs, so quick recap of transformations. This is a nice chart from the book. It's on page 418 of our textbook. If you need it, you can also just pause the video and copy it down if you miss it. I'm going to go through it pretty quickly. Vertical shifts or translations are accomplished by adding or subtracting a number at the end. Horizontal translations are accomplished by adding or subtracting a number within the exponent. So in general function, this would be, f of x plus c or minus c. For exponential functions, that's something that happens in the exponent is going to cause that horizontal shifting or stretching or whatever. Reflections over x-axis affect the y value, so that's outside of the function. And reflections across the y-axis actually affect the x values, so that's going to happen in the exponent. So pay attention to the difference between those. It really does work the same as all other transformations. It can just be sneaky to sort of spot where that negative is. A vertical stretch is a coefficient out front, and a horizontal stretch is a coefficient on the x, just like other functions. And remember, when you have a horizontal stretch, you actually divide x by c. You're dividing by c, not multiplying by c like you would with a vertical stretch, so that if you have a number like 2 is the c value, it actually turns out to be a horizontal shrink. Remember that sort of backwards operation. Same with horizontal translation. Remember that f of x plus c actually moves you to the left, so anything that affects the x values operates backwards. And we've covered that a lot in other sections, other videos. But if you want to see more, just come see me. We'll talk about it one-on-one. Also, remember that when you're doing transformations, the order is important. If you do transformations in the wrong order, you'll get a different graph. Here is the order that we have grown accustomed to. Do x transformations first, and then of the x transformations, do your horizontal translations left and right. Horizontal dilations, stretching or shrinking this way, and then any reflections about the y-axis. Then you can start shifting the y values. Start with any reflections about the x-axis, then any vertical dilations. I'm using this for dilations, and then any vertical shifts up or down. Some complications. Technically, these dilations and reflections can happen in either order. And also technically you can do x transformations and y transformations in either order because they each just affect a single coordinate of the coordinate pair. That said, if you just want an order, here's an order that works that will always work. And so you can just adopt this order of all the six transformations that you see. So a general approach then with all of that in mind for exponential graphs and transformations, you start with a parent, which remember depended on what your base value was, then plot your y-intercept, at least one other point, maybe two, and the asymptote. And then the 2 to 3 points and asymptote all get transformed as you draw the steps of transformation. We're going to do 3 to 4 examples to show you what I mean. First example, y equals 3 to the x minus 1 minus 3. So, in the x minus 1, that's our x transformation. So this is telling us to shift x to the right by 1. And the minus 3 is telling us to do y down 3. We also notice that we have a base of 3, and that will affect how you sketch your parent. So first sketch the parent graph, 0, 1. And I'm going to go 1, 3 as my 2 key points on the graph. I can maybe also put 1/3 over here, and also that horizontal asymptote. Since I'm shifting down 3, I am going to have to shift that asymptote downwards. So here is the base parent graph. You're going to get really good at drawing a base exponential parent graph. Now we'll shift everything to the right by 1. The asymptote does not shift 1, but the y-intercept will shift 1, and the general shape of the graph will remain the same. Oh, that point's in the wrong spot. That's a little better. Now we're going to shift everything down 3. When we shift down 3, we do shift the points down 3. That point was at 3, so that's going to go to 0. How nice. We also shift the asymptote down 3. This is the one major thing that folks will miss. It can actually be easier, let me actually undo this, to move the asymptote first, because then you can sort of treat that as your new axis for sketching, right? If I now have this baseline, I don't have to count down, I can just count how far above the axis were these points. So, instead of counting down 2, I'm actually just counting up 1 because this point was up 1. So that's a little tip. And then you can sketch your full and complete. Oh, I still have that option on. No good. Sketch your full and complete graph. Something like this. All right, for the second example, let's look at a y equals -1/2 to the x plus 1. So first thing I notice is there's nothing else up in the x, so there's going to be no x transformations at all. But I do notice that I have base equal 1/2, so this is going to be a decay graph. I also notice there's a negative out here, so that's going to reflect the y values over the x-axis over the x-axis, so we'll call this an x-axis reflection. And we have a plus 1, so we're going to shift y up 1. So one of the challenges here is just making sure you have a good graph of the base. We always go through 0, 1, 1, 1/2, and -1, 2. We also have the horizontal asymptote at 0, which I'll just kind of do like this. You only really need to draw it on the side it's going to apply, but I like to draw the whole thing. So the parent graph looks something like this. That's just the 1/2 to the x graph. Then we're going to reflect it over the x-axis because we always do reflections before vertical shifts. So then this graph will reflect down here. The asymptote stays at 0 because it did not shift, so the graph is still down here. And then we're going to move everything up by 1. Now when we move everything up by 1, we do need to move the asymptote. So I'll draw the new asymptote, y equals 1, and then, just like I said before, after I draw the asymptote, I'm moving things with respect to the asymptote. So up 1, so this should be 1 under, this should actually be matching with that point. So sometimes, right, you can hit the same points again. Your final child graph should look something like this. One comment about this is when you have a vertical reflection of an exponential decay like this, it can sort of look like growth, right? The function is growing. I don't think this would make much sense to describe this as exponential growth. It's still a decay function. It's just been switched around or moved around in the plane. Okay, next graph is 4 times 1.5 to the x. And this might look really simple, but there's some complications here. First, make sure we identify the base correctly. So the base here is 1.5, so we are going to be looking at growth. Even though it's a decimal, it's greater than 1, it's causing that growth. Then we have a 4 out front, and that's the only transformation. Remember, when you have a 4 out front, that's a vertical stretch. So we have a base of 1.5 and a vertical stretch by a factor of 4. Let's see where that gets us. Start by drawing the base. So I'm going to try to be sort of specific here. So this is 1.5 here, or 0, 1, and this is 1, 1.5. We'll plot here. I just want to get a good value, so I'm going to do 1 divided by 1.5. Oh, 2/3. I could have done that without the calculator, but 2/3 will be the value to the left. That's the negative value. There's a little negative there, do you see? So here's our parent function, looking something like this. Asymptote still at 0. And there's no shifts here, so that asymptote is just going to stay at 0. But let's actually apply this vertical stretch. Remember, how do you apply a vertical stretch? You multiply all the y values by that number. So 0, 1 is going to move to 0, 4. 1, 1.5 is going to go to 1, and 4 times 1.5 should be 6. So this is 1, 6. And then over here on the other side, 2/3 times 4 is 8/3, which is 2 2/3. So 1, 2 2/3. So something like this. The asymptote, though, stays the same. So this graph would look something like that. So that's a vertical stretch. Vertical stretches and shrinks, and same with horizontal stretches and shrinks, which we don't have in this video, but you might have to do on a problem set. They can be difficult to graph. Make sure you have a good scale set up, and make sure you're just plotting specific values for your points as you work. Here's the reason I chose this graph is in previous classes, you might have thought of the exponential functions as actually being of the form y equals a to b to the x, where a is the initial value. And in fact, when we looked at geometric sequences, or if we haven't looked at them yet because it's a different year, then we maybe looked at, we will look at a sequence, an is a1 times r to the n minus 1. So we notice that that's the initial value. Well, in an exponential function, the parent, there is no initial value, or I guess I should say the initial value is 1. So in this context of an exponential function, that vertical stretch value does tell you the initial value of 4, but only because it's a vertical multiple of 0, 1. It's been stretched up by a factor of 4 to move that point up to the initial value. So just the connection to other types of sequences or other versions of the exponential function that you've seen. Actually, it's just a transformation of a single parent function with that common base. All right, last example, and this is maybe the one that's going to prove the most challenging. Y equals e to the 3 minus x. This looks like the simplest one, but there's a couple complications. First, base is e. Now remember, what is e? We're actually going to talk about that in a second after we make the graph, but for now, all you need to know is that e is a number approximately 2.7. So it is greater than 1, so we're going to be looking at growth here. And it doesn't actually matter that e is 2.7. We're going to treat it just like any other exponential growth. However, the main trick here is we have 2 input transformations, 2 x transformations. So we can think about this as e to the negative x plus 3. Might be a more useful way to see it, although most books will give you it in 3 minus x form. And that helps us see what's going on. We would first do the plus 3. Remember the order we wrote? So that's going to go left 3. And then we'll deal with the negative. So that's going to go reflect over y. So we're going to go left 3 and then reflect over y. And it has to be in that order to give us the correct result. All right, so how do we make the graph? Well, start with our point 0, 1. And we'll go to the point 1e. So, you can plot it approximately at 2.7, but I'd like you to label it as 1, e, because that's the value it is. Over here would be at 1 over e, which is, about 1/3. So this is the child graph. The asymptote is still at 0. That doesn't seem like it's going to change, so we'll just keep that y equals 0 line. Then we're going to go left 3. So all of these points are going to go left 3. Remember, it's x plus 3 moves things to the left. It's that backwards situation going on. 1e's goes over here. And now we have to reflect all the points. Remember, when we reflect over y, we don't just change it to a decreasing function. We actually have to reflect across the y-axis. So reflecting all of these points across the y-axis, we're going to get this. It's actually turning into an exponential decay function in the end. It shouldn't surprise you that this is decay. Remember what we talked about when you have a negative on the variable in the exponent, that usually does give you decay. So here's we said that that's because of a transformation. This is what we were talking about earlier. So e to the 3 minus x, just remember when you have these double input transformations especially, the order matters. The order always matters, but the order really matters with these double input transformations, because if you did these in the opposite order, actually, why don't we check that out? If we reflected over y first, so we'd be doing this, and then we went left 3, we'd be in the wrong quadrant, folks. It'd be a completely different graph. So because we went left and then reflected, we actually ended up kind of going net to the right. But that order does actually affect that transformation. Okay, a good place to end this video is to maybe give you a couple more facts about that number e we just used. And the key facts are the top 4. So, e is a number, not a variable, right? It's not like x. E is more, we'll say most, like pi. So if you're comfortable using pi, you should be comfortable using e. Now, they come from completely different sort of applications, although there are some equations that relate e and pi, but it operates in the same way. It's an irrational number. Irrational, remember, means that its decimal expansion never terminates and never repeats, so it will never cycle back on itself. Our approximation that we can use is approximately 2.7. That's as many digits as we need for e. Here are some more digits if you like. I'll post this link, or you can search it up, to give you about 2 million digits right there. So, you can have as many digits as you want. I will tell you, even NASA, who is the source of this data, they use about 10 digits for their calculations. I think 15 now. And even physicists that are trying to do the fundamental constants of the universe, they use about 30 digits, which is plenty for pretty much any reasonable level of precision. So you can use 2.7, or if you're feeling really precise, 2.71, and that will be plenty enough for us. E is the base of the natural logarithm. We're going to use that a lot, but that's like one of its key components. So these are probably the 3 key ideas about E. Here's some other facts about it, though. It is named after a Swiss mathematician named Leonhard Euler. It looks like Euler. It's pronounced Euler, like oil. He's always, all the pictures of Euler, they don't look like he's giving you like a weird little side eye. Invented a lot of stuff. E stands for Euler. He didn't name it that. People coming after him named it that, as a tribute. So sometimes it's called Euler's number. It is calculated by computing the ratio, or the limit as n goes to infinity of the ratio 1 plus 1 over n to the n, which you could think of as continuous compounding interest or growth. So it does kind of come from an exponential situation, but it's a more complicated exponential situation. You can see that if you take that quantity 1 plus 1 over n to the n, 1 plus 1 over 1 to the 1, that's just 2. So that's the first line. But 1 plus 1 over 2 to the 2 is 1.5 squared. That's with the 2.25, right? So you can see it starts at 2, it goes 2.25, 2.48, and grows and grows and grows, and you might think that that's going to grow forever, But if you actually take enough digits of it, it doesn't grow forever. It converges to e. So this is like one of those infinite converging sequences. It's not specifically a specific kind of sequence, but it converges to this value of e. And in calculus, e is most important because it computes its own rate of change. Yeah, it's the only function that does this for every x. So the slope of a tangent line at 4 is e to the fourth at y equals e to the fourth. And of course, you'll learn more about that next year when you do this. But that's the only function that does that for all x values, or at least the only easy function that does that for all x values. So it's actually a very convenient function to use. And that's one of the reasons that we give it its own logarithm and its own name and its own number and such. So there's just some fun facts about e to kind of close this video out. So that's the end of this video. What do you need to know walking away? I know there's been a lot of material here. I would say for exponential functions, you need to know what the graphs look like, how to tell if a function is exponential or not. You need to know the basic transformations of all functions and the order they go in, and then how to apply those transformations to exponential functions. You should also be passingly familiar with the number e, basically know that it's approximately 2.71, and that's about it, and be comfortable working with that e because we will use it all the time in Chapter 3. Let me know what questions you have, folks. Thanks for watching, and I'll see you all next time.